Alright, so today we're learning section 1.7, rational expressions. So we're going to learn about simplifying rational expressions, combining rational expressions, and simplifying complex rational expressions. So we need all this information before we cover 2.5, where we're solving rational equations. And so usually it's better to cover this right before that section, so that's why this section appears in the chapter of 2 when we teach it. Definitions. A rational expression is the quotient of two polynomials, p over q, that is a fraction where the numerator and denominator are both polynomials. The domain of an algebraic expression is the set of all real numbers for which the algebraic expression is defined. A rational expression will be defined everywhere except for where the denominator is 0. In this case, q equals 0. Q is the polynomial name on the denominator. So for this first exercise, we need to find all the numbers that must be excluded from the rational expressions domain. So here we're only concerned with the denominator. Now, if anything cancels or anything, happens, or simplification happens after that, that's afterwards. But first we need to find out what the domain is. So normally the domain would start out, domain is all real numbers except, and then we have the first rule, zeros of the denominator or the second rule, negatives under even radicals. And we'll talk more about that in 2.6, even radicals. So there's an implied domain here. It's not stated. So we assume it's all real numbers except for when these two things occurs for us right now. And so right now we need to find when x squared minus 36 equals 0. Two ways we can solve this. We can solve this either by using the factoring the difference of two perfect squares, or by the square root method. Either way is fine. And here we're going to have x equals plus or minus the square root of 36, which is 6. So that means the domain is all real numbers except x cannot be equal to 6 or negative 6. And it shouldn't matter which order you put this in, Hawks. Technically, you want set or braces around these, but usually Hawks gives you those. You don't have to actually put those in. If it wants them, it'll tell you in the practice. If you try to put curly braces in to denote a set of two answers, it won't let you put them in if they don't want you to for your homework. So, and then if you were to write this in interval notation, we have the following: all the numbers from negative infinity all the way up from negative 6, not including negative 6, union negative 6, because that's right on the other side of negative 6, that parentheses right there, not including 6, union all 6 all the way up to positive infinity. So we cut two portions of our real number line out, so that's why it's in 3 pieces. Simplifying rational expressions. Number 1, we factor the numerator and denominator completely, find all the excluded values, cancel out any common factors from the numerator and the denominator, exclude the values from the original expression that are still excluded in the simplified expression. So in other words, we want to find the excluded values first before we cancel. So here we have an exercise 2. We need to factor everything. So we always look for greatest common factors first. And so we look at these, and both of them have an x to the squared power in them. So that leaves behind, when I divide that x squared out and x minus 3. Now here's the thing. Usually when they want you to work these problems, a factor that they have in the numerator will also appear in the denominator and vice versa. So if you factor the easier one, the numerator and denominator, usually one of those factors will show up because they want you to simplify. So using that knowledge of how math works and how math problems work, we can probably say that one of these factors is going to be x minus 3. But let's make sure, let's go over here and let's say factors of 24 whose difference gives me 5. Well, let's look at that. So I got 1 and 24. 2 and 12, 3 and 8, and then we have 4 and 6. So we can see the difference between 3 and 8 will give us 5. So, and it's like we thought, x minus 3, and then we have x plus 8, because the negative 3 and positive 8 gives us plus 5, negative 3, positive 8 gives us negative 24. And also, like I said, we probably thought there was going to be an x minus 3 in there, because otherwise we wouldn't have anything to cancel. So that's going to give us, well, now from here we find out our domain. So the domain is going to be that first situation of our rules where we're going to say anything that gives a 0 in the denominator. So in other words, we have x cannot be, or the domain, right over here, domain is all real numbers. X is not equal to, in this case, positive 3 or negative 8. And you can just look at that by examination. You can see that positive 3 here will give you 0, negative 8. If you need to set each factor equal to 0 and solve, you can do that as well. Say x equals minus 3 equals 0, and x plus 8 equals 0, and you can see how you get those zeros. Now to cancel and to simplify. So to simplify, we cross out our x minus 3s. Find out which markers I'm running out today. A lot of them. Anyway, those cancel. And so we have x squared over x plus 8. So here we have our simplified algebraic equation. Now these are algebraically equivalent. They give the same numbers when you put them in, but they are not functionally equivalent because they have different domains. This algebraic expression is no longer restricted by 3 because we canceled those out. All right? But we lose that information if we don't find out the restrictions first. So find out the restrictions for first so we don't lose that information. Remember, if you change the domain, you change your function. While they may be algebraically equivalent, they don't have the same domain. All right. Multiplying and dividing. So multiplying is simplifying all the rational expressions completely. Multiply the numerators together and the denominators together, leave in factored form. Dividing, we invert the second fraction, the second rational expression, and multiply the two expressions together. So we just kind of went straight to division, because division is the same thing as multiplication, only the additional step of flipping this fraction, the second fraction right here, because it's after the division symbol. So we're still going to have our x squared minus 2x plus 1 over x to the third plus x times, and we flip this and we're going to get 3x squared plus 3 over x squared plus x minus 2. And so now I'm going to factor. So that's my next step, is factor. And so that's going to, before I multiply anything together, I don't want to make my life more difficult, because if I multiply these trinomials together, I'll never be able to get them apart. So the first one, I need two factors that multiply to give me x, so x squared, so I'm going to need x, and 1, and they have the same sign whose sum is negative 2, so that's going to be negative 1 and negative 1, so that happens twice. And then I'm going to factor out an x from this denominator term here, in the first fraction. So an x comes out, so I'm x squared plus 1. Remember, this is not the difference of two perfect squares, so that does not cancel. I can't cancel out that x squared plus 1. And then I'm going to say that's multiplied by, I can factor 3 out of this numerator, the second fraction. So I get x squared plus 1. 3 comes out front. And then this bottom term right here, I need two factors. that multiply to give me x squared, so x times x, and multiply to give me negative 2, but add to give me whose difference is positive 1. So one thing that would do that would be x plus 2 and x minus 1. And once again, knowing information we know about how problems are set up in general, we can find out, hey, what's probably going to happen here is my x squareds will show up, or my x squared plus 1 or an x minus 1 will show up in the numerator denominator. So I cancel each one of those respective ones out. And then I multiply it back together, or I multiply it in the first place. And I'm going to get 3 times x minus 1 over x times x plus 2. And here is just a simple monomial. You always want to simplify your numerators. Your denominators can usually stay factored in Hogs. Usually when I hand grade test, leaving your denominators factors unless explicitly told to multiply them out is fine. But numerators, always need to simplify those. So we get 3x minus 1, or minus 3, excuse me. Let me distribute that. And then at the bottom, we're going to get x squared plus 2x. And I just multiply this out because it was a nice monomial. I can multiply it out easily. And nothing cancels. We're done canceling for that one. And here we really wouldn't state our domain because we're dividing. We're doing it algebraic. Usually they want you to state your domain is when you're solving an algebraic, a rational algebraic expression, or you're just looking for the exclusions. They'll ask you for that. Find the least common denominator. When we add or subtract rational expressions, we want to use the smallest common denominator. We call this the least common denominator, the LCD, or the least common multiple of the denominators, the LCM, usually called the LCD. Completely factor each denominator, express repeated factors in exponential form. List each factors the greatest number of times it appears in any one denominators. Multiply the listed factors together to determine the LCD. Leave the LCD in factored form, because if you multiply it back out and you need to cancel later, it's just more work for you. So it says find the least common denominator for the two denominators. So it's assuming we have two fractions out here. We have 1 over x squared minus 6x plus 9. And we want to do something, want to add or subtract or whatever, to 1 over x squared minus 9. So they're saying these are our denominators, so we need to find the least common denominator for both of these. So we need to factor them. So I'm going to write them as is right here. And so now I'm going to factor them. So factored, I need two factors that multiply to give me x squared, so that's x times x, and 9, who have the same side who sums to 6. Well, that's easily going to be x minus 3, x minus 3. So that's a repeated factor. And here, this is a difference of two perfect squares. So it's going to be x minus 3 and x plus 3. So now we can see, well, let's write this in their most condensed form, the exponential form, if they have the same, let's use exponents to write them with. If they have the same factor more than once, you can write that as x minus 3 squared. And this is still going to be x minus 3 times x plus 3. Now remember, we want the unique, the highest power of each prime factor, so each different factor. And here the highest power is going to be of x minus 3 is x minus 3 squared, and the highest power of x plus 3 is going to be x plus 3 here. So that means our LCD is going to be equal to x minus 3 quantity squared, because I need two of them. And then since I already have two of them, I don't need the one from here. And that means x plus 3 here. All right. Now, one thing students do is they assume that you have to pick one from each list, and that's not necessarily true. It often happens, but you could get a denominator that is already the least common denominator of your entire expressions. That could totally happen. Adding, subtracting rational expressions. We find the least common denominator. We write the equivalent expressions with the least common denominator as the denominator by multiplying any missing factors by both the numerator and denominator of that fraction. Add, subtract the numerators, replace over the LCDs if possible to reduce and if possible reduce the result to lowest terms. So you always want to make sure you have it in the simplest terms. It's easier to read, easier to grade, easier to deal with in general with polynomials. So it says simplify the following. So off to the side somewhere, let's find our LCD. Grab another sheet of paper. So finding. So I have my two denominators. I have x squared minus 10x plus 25. And then I have a 2x minus 10. And so factoring this completely, once again, we get x minus 5 times x minus 5. Factors nicely. You can see that pattern it has. And then we're going to factor out a 2, and so we get an x minus 5 here. So we have x minus 5 quantity squared, and that's going to be just 2 times x minus 5 for the second one. And so these are now factored completely, so we pick the highest power term of each unique prime factor. So I'm going to need x minus 5 squared, and I'm going to need a 2. All right. So that means my LCD is going to be x minus 5 quantity squared times 2. I'm just leaving a factor so we can see what it is right now. So now with that information, I'll put that up here somewhere. We can start adding these together. So since I've already factored the numerators, the denominators, I'm going to factor them again. So I'm going to have, I'm going to use that information. So I'm going to have x over x minus 5 quantity squared. I'm going to say minus, and then I'm going to have x minus 4 over 2 times x minus 5. Now, I left a space here because I need a 2 for this to be the least common denominator in the denominator here. So I'm going to multiply the top by 2 and the bottom by 2. So I didn't change they didn't change the value of my fraction. And over here, this is missing one of my powers of my x minus 5. So I'm going to, in order to make this x minus 5 squared, I'm going to have to multiply top and bottom by x minus 5. X minus 5. And so over here, I'm going to get 2x over, and I'll leave the denominator factor because something could cancel later on. Don't want to multiply that out. And then I'm going to say minus, I might be able to fit it here. This is going to be 2x minus 5 quantity squared now in the denominator. But now I'm going to have, for this one right here, I have to FOIL this out. So x times x is x squared. I'm going to have x times negative 5, which is negative 5x. X times negative 4, which is negative 4x. So it's minus 9x. And then I'm going to have negative 4 times negative 5, which is positive 20. So now that I've done that, I'm going to say, well, we have 2x minus, I'm putting it all over the same denominator now because they have the same denominator. That's the whole point. Don't want to forget my x there, my 9x. And that's going to be in the denominator. It's going to be my least common denominator, 2x minus 5 quantity squared. And so I need to distribute this negative. I always take a separate step to do that. It'll be negative x squared minus, now that's plus 9x minus 20 all over my 2x minus 5 quantity squared. And then that equals negative x squared plus 11x minus 20 all over 2 times x minus 5 quantity squared. Now real quick, we want to make sure nothing cancels. I can't cancel a 2. I can't bring a 2 out from everywhere. Is there an x minus 5 factor in here? Well, there's no, if I have 20, the factors of 20, there's no factors of 20 since they have the same, they have different signs. The difference is going to be 11. The difference here is 19. The difference here is 8, and that's 1. So there's no way to get that there. So it doesn't factor. So we're done with that one. Complex rational expressions. Complex rational expressions is a rational expression that contains, a complex rational expression is a rational expression that contains rational expressions in the numerator and or the denominator. In other words, basically your fractions have fractions. So this is something that may come up an expression like this later on, where we have 1 over x plus h minus 1 over x, and that's all in the denominator, or all in the numerator, all over h. So remember, fractions are like grouping bars. So in other words, this part would be done before this part right here. Another way of writing that could be, 1 x plus h minus 1 over x. And this all divided by h, or multiplied by 1 over h. It's another way to say it. Is that how I want to say it? Yeah. Finding the LCM of, so simplifying complex rational expressions, finding the LCM of all the denominators and the numerator and denominators of the complex fraction. So basically what you're doing is you're finding all the denominators of the numerator and denominators of all the fractions at once, multiply the numerators and denominators by the complex fraction by this LCM, simplify both the numerator and denominator, reduce to the lowest terms. So there's a couple ways of doing this. Some ways are one way is easier than the other. The first way is to, like I said, rewrite it as, rewrite this equation right here as 1 over x minus 3 over 2, and then that's going to be divided by, and then you're going to have 1 over x plus 3 over 4. Now, this only works well if you can simplify these fractions really easily, because when you flip this, you're just going to get another complex rational expression right here when you flip and multiply, and you don't want to do that. So the easiest thing to do here would probably to find the least common denominators of everything first and do that all in one big step. So over here you want the least common denominator of everything. So we have an x, a 2, an x, and a 4, and a 4 is just 2 squared. So I picked the highest prime factors of each one. So I'm going to pick the x, and I'm going to pick the 2 squared. And that's all I need. I don't need another x because I already have an x to the first. I don't need a 2 because I have a 2 squared. And so my least common denominator is just going to be 2 squared times x, or basically 4x. And I just wrote it 4x out there because it's easier to see, easier to write like that. So I need to multiply both top and bottom by the least common denominator. Now what I like to do here, since I have to multiply it both, I like to line up my fraction bars. So here I'm going to multiply, instead of just saying I'm going to multiply by 4x in the top over 4x in the denominator, to line up my fraction bars, I like to do that. So now all my fraction bars are lined up, and I make sure everything is going where it needs to. And then remember, this is essentially multiplying by 1. I haven't changed the value of anything. So now when I multiply this across, I'm going to get 4x over x minus 3 times 4x over 2 all over. And this is going to be 4x over x plus 3 times 4x over 4. I'm going to go in and I'm going to cancel any terms that cancel right off the bat. So you see how these x's will cancel right here. This 4 will cancel with that 4. And right here, this 2 will cancel if I make this 2 right here. Cancel, cancel. There's still a 2 left. So in other words, let's rewrite that so it's easier to look at. So I'm going to have 4 minus, and this is going to be 3 times 2x divided by, because I got rid of all the denominators in the numerator, 4, and this is going to be, my 4's cancel, so I'm just going to have plus 3x. So that's going to give me 4 minus 6x all over 4 plus 3x. Now remember, we want to simplify if possible, and I know a lot of students see 4s and 3s and x's and they just want to start canceling. I have students say cancel this to -2, which would be very, very unfortunate. Because if you want to cancel something out, you have to bring it out from the entire term. So if I want to cancel this 4, I have to bring out 4 out from every term in the numerator, every term in the denominator. Can't do that. Same thing with if I want to divide out by 3 or an x. I have to bring those outside and then cancel them. And since I can't do this, this is in simplest form, it doesn't simplify anymore. Once again, this is another expression where if I had like a single expression that I was dividing by instead of a sum of fractions or difference of fractions, you know, it might be easier to look at it like x minus 3 and then divide that. And then if this is one expression, we could flip and multiply. I'm just showing this to students because some students were taught this way, and you can still do it this way. But remember, if you flip this second fraction to multiply, you're going to get 1 over 2x minus 8. And then you're just back where you started from, right? So we don't want to do that if we have fractions in the numerator, fractions in the denominator, and we're adding and subtracting those fractions, because flipping those fractions aren't useful because we're still adding and subtracting them. So we're going to do the same thing we did before with the least common denominator. I'm going to need an x. I have x squares, I have x, I have an x to the third. So the highest power of each unique prime factor, well, I only have one unique prime factor, that's x, and x to the third is the highest one. That's the only one I'm going to use. So I'm going to multiply top and bottom by x to the third over 1, or x to the third over 1. Once again, you don't have to put it over 1. I just do it so all my fraction bars lined up. It's easier to see, easier to keep track of things. So I'm going to say 3x to the third minus 6x to the third all over, and this is going to be x minus, oops, not all over, excuse me, I haven't gotten to that part. Let me rewrite that. So let me rewrite that and say this is going to be 3x to the third minus 6x to the third. This is over x, and this is over x squared, all over. And then I'm going to have 2x to the third minus over x minus 8x to the third over x to the third. I'm going to go through, I'm going to cancel. So here I can get one of these powers to cancel. Here I'm going to get 2 of these powers to cancel. Here I'm going to get 1 of these powers to cancel. And here all 3 of the power cancels for x. So we rewrite that as, so we have 3, and this is going to be x squared still, minus 6, and this is going to be x to the first. You don't need to write that one. And then we're going to have 2x to the second minus 8. And looking at this, you might think, okay, well, I can't bring an x out. I can't bring a 2 out because that's 3. But what we can do is the denominator factors and the numerator factors. So let's factor them. Before, ours didn't factor, but let's factor and see what our factors are. So I can bring out an x from every term. Matter of fact, I can bring out a 3x from every term in the numerator. And so I'm going to have 3x, and I'm going to leave behind an x minus 2. And in the denominator, I can take out a 2. But when I take out a 2, notice I'm left with 2x minus 4. 2x minus 4 is the difference of 2 perfect squares. This is going to be x minus 2 and x plus 2. So just write down that intermediate step if you need to. That's fine. Now we can see that things cancel. So what do we get canceled? We get our x minus 2's to cancel. And so our final answer for this would be 3x all over 2 times x plus 2. Once again, the denominators can usually stay factored. The numerator has to be simplified. But here, since it's just a monomial, I'd write it as 2x plus 4. And that's our lesson for today. Hope you all have a good one.